Somewhere out there in the universe, there's a place where absolutely nothing, not light, not matter, not even the whole concept of escape can survive. It's the absolute extreme of our reality, a black hole. We've spent decades studying the sheer terror of this cosmic trap, right? A place where everything enters and nothing leaves. But what if there's a bizarre mirror image to all that absolute darkness? Imagine, if you will, the exact opposite. A place that only expels. We're talking about a cosmic fire hose of matter and energy erupting endlessly into the universe and breaking the laws of physics in ways that should absolutely keep you up at night. Today in this explainer, we're going to explore the universe's most extreme opposites. We are putting the black holes we know up against the white holes we've only theorized about. Let's get into it. Okay, let's dive into part 1, the absolute darkness. So let's ground ourselves in how a black hole actually forms. It happens when a truly massive star, we're talking something typically more than 20 times the mass of our own sun, finally reaches the end of its life. Step 1, it exhausts its nuclear fuel. Without that outward pressure to hold it up, step 2 happens. It violently collapses under its own staggering gravity. And step 3 is where things get crazy. The core literally crushes itself down into an infinitely dense, tiny point called a singularity. Now, what's really fascinating here is the boundaries surrounding that singularity. This is the event horizon. And it's important to understand this isn't a physical solid surface you could go up and touch. It's a mathematical boundary. Once you cross it, the laws of physics as you know them just completely stop applying to your survival. Because the escape velocity at this boundary actually exceeds the speed of light. And since nothing travels faster than light, absolutely nothing comes back. No radio signals, no distress calls, no X-rays, literally nothing. And the scale of these objects, it's just terrifying. Black holes come in all sorts of sizes, from stellar ones that are just a few times our sun's mass up to supermassive monsters. Take Sagittarius A star, for example. That's our own galaxy's central black hole. It clocks in at a staggering 4 million solar masses. Just try to picture that. 4 million suns crushed into a single region of space. And the crazy thing is, we actually know they're real because we've looked right at them. In 2019, we captured the very first image of a supermassive black hole at the heart of galaxy M87, which is about 55 million light-years away. It showed this glowing orange ring of superheated matter, and right smack in the center, pure absolute darkness. That one single photograph basically confirmed a whole century of theory. Let's move on to part 2, the physics of falling in. All right, picture this because it's one of the most fascinating contrasts in all of physics, gravitational time dilation. If I were watching you fall into a black hole from a safe distance outside, time itself actually runs slower in stronger gravity. So I would literally see you slow down and stretch out over the event horizon. You'd look frozen in time, almost like a cosmic screensaver, as your light gets redshifted and dimmer until you completely fade away. But from your perspective, falling in, time feels entirely normal. You would cross that horizon in an instant. And once you're inside, the geometry of space-time becomes completely mind-bending. Actually, mind-bending doesn't even cover it. A singularity isn't just a physical place you're falling toward anymore. It becomes a moment in time. All paths through space-time inside the event horizon lead directly to the singularity. You can no more avoid hitting it than you can avoid tomorrow. Now, how you actually meet your end depends entirely on the size of the black hole. Near a smaller, stellar black hole, the tidal forces are incredibly violent. Gravity pulls so much harder on your feet than your head that you would be stretched vertically and compressed horizontally into a literal strand of subatomic pasta. Seriously, the official scientific term for this is spaghettification. But ironically, a supermassive black hole is much gentler at its horizon. You could drift right across that point of no return and not even notice until it was way, way too late. All right, let's flip the script. Part 3. The cosmic mirror. I want you to take everything we just talked about, all that crushing, inescapable gravity, and just flip it. And I mean this quite literally. A white hole is a black hole running in reverse. And I don't mean that as a metaphor, I mean it mathematically. Einstein's field equations, which are the absolute core of general relativity, are beautifully time-symmetric. That means the exact same math that perfectly describes matter falling into a black hole also perfectly permits a solution where matter is ejected from a singularity. So we define a white hole as a mathematically reversed region of space-time. It's a place that matter and light can only exit and absolutely never enter. This was formalized back in the 1950s using what's called the Kruskal-Shakaris extension of the black hole math. Basically, what that means is that buried in the equations of every single black hole is its theoretical mirror image. To put it simply, think of the event horizon of a white hole as the universe's most aggressive bouncer. It works exactly like a one-way valve, but pointing entirely outward. Nothing, no matter how incredibly hard it tries, can ever fall in. Everything is violently pushed away. And this connection gives birth to one of the most famous concepts in all of sci-fi, the Einstein-Rosen bridge, which you probably know better as a wormhole. The full math of a non-rotating black hole actually features 4 regions: the black hole, our universe, a white hole, and a parallel universe. The black hole and the white hole are connected throat to throat, forming this elegant tunnel in space-time. Unfortunately, the math also shows this tunnel would collapse far faster than anything could ever possibly travel through it. And this brilliantly illustrates our next section, Part 4, the ultimate showdown. Let's compare them directly, side by side. Origin. Well, black holes form from observable stellar death. White holes? Nobody actually knows. Nature hasn't shown us one yet. Direction. Black holes relentlessly consume, pulling everything inward. White holes endlessly expel, pushing outward. What about stability? Black holes are incredibly stable, lasting longer than the current age of the universe, just slowly evaporating via Hawking radiation. White holes, however, are theoretically violently unstable. Any matter approaching one could cause it to collapse instantly. And, of course, observability. We have direct images and gravitational wave evidence of black holes, while white holes remain purely theoretical. But here is the real kicker, the deepest tension: entropy. Black holes obey the second law of thermodynamics. They increase entropy. A white hole, because it's running in reverse, would locally decrease entropy. It fundamentally breaks one of the most inviolable laws in all of physics. Which brings us to the big question in Part 5. Could they be real? Believe it or not, some physicists don't think it's science fiction at all. In fact, here are 3 stunning theoretical candidates for where white holes might actually be hiding in plain sight. First, a theory called loop quantum gravity suggests that as a black hole slowly evaporates over massive astronomical timescales, it might eventually transition into a white hole. Second, how about the Big Bang itself? Think about it for a second. A singularity that only expels matter and energy, the ultimate one-way door from which our entire universe erupted, that describes a white hole perfectly. And third, some researchers propose that those unconfirmed gamma ray bursts, literally the most energetic explosions we see in space, might actually be the signatures of white holes erupting. So, the crucial point is this: if that first theory holds true, a white hole phase might finally solve the infamous black hole information paradox. For decades, physicists have endlessly debated whether information consumed by a black hole is truly destroyed forever. But if a dying black hole turns into a white hole, it could theoretically release all that consumed information right back into the universe. Ultimately, white holes are the shadow of everything we know about gravity. They are totally permitted by the exact same equations that govern black holes, yet they remain unseen, forbidden by our current understanding of thermodynamics. But remember this: not too long ago, black holes were just theoretical oddities hiding in Einstein's math, too. In physics, when the math says something can exist, history has a remarkable habit of proving us right. So I leave you with this question to chew on. What else is hiding in the math, just waiting for us to open our eyes and see it?